Morning everyone. So recall that in the last classes we have discussed the combinatorial problems, mainly arrangement and selections with repetition, without repetition. Today we are going to see some binomial identities. So to begin with, why CNR is said to be a binomial coefficient. So to understand how binomial coefficient come into the picture, let us consider the following expressions. So if you see 1 plus x cube, you will see that there comes the 8 terms. So first thing is why 8 terms. So since there are 3 positions and each one has 2 choices, a or x, that's why it is 2 raised to the power 3. So this is the one question. And the other question is that when you write the sum, then you will see that the coefficient of a cube is 1, a square x is 3, and so on and so on. So how does we compute this coefficient? Again, here you will see that let's focus on x. So what we are saying is that out of 3 positions we are choosing the 1. So how many formal products in the expansion of a plus x cube contains kx and 3 minus k's. So this is what we are looking for, or we are looking for the coefficient of a raised to the power 3 minus k, x raised to the power k. Yes. So since the sequence is 3-letter sequence of a and x, so we are simply asking how many 3-letter sequences are there with kx, because the remaining would be filled by a's. So that would be 3ck. So if 1x is there, 3c1, 2x is there, 3c2, and so on. And that's why we can write the expression in this form. It means if we generalize it, then in a plus x raised to the power n, we can say that the number of n letter sequences formed by kx, which means the coefficient of x raised to the power k and a raised to the power n minus k, is c n k. And if I put a is equal to 1, then it becomes the binomial theorem, where the coefficient of, because a is 1, so coefficient of x raised to the power k is c n k, and that's why we call them the binomial coefficient. Now let's write down the equivalent identity for the number of ways to select a subset of k objects from n, which we know that it is nck, is equal to number of ways to select a group of n minus k objects to set aside, which means you can see it as also that number of ways to select n minus k object from n object, which is c n n minus k. Yes, so we already know that these two identities are same, but how do we prove it? So let's move to the next question, which says that prove the following identity. Cnk is n minus 1 ck plus n minus 1 ck minus 1. Now you may be able to prove it algebraically by simply substituting the values, but I want to see the combinatorial proof, which means in the terms of the number of the ways. So the left hand side is straightforward, number of ways to select k people or k objects from n objects. What is the justification for the right hand side? So in the right hand side you can say that one time we have k and the one time we have k minus 1. So let's say that there are n people and we want to form a committee with k people. Yes, and then there is a person p which is either in committee or not in committee. Both the possibilities are open for this person. Now what will happen if he is in the committee? If he is in the committee, he is already there. So you need k minus 1 person, and out of n minus 1, because he is already there, so we should not consider it. If he is not in the committee, then need k persons in the committee, but out of n minus 1, because you already know that p is not there. This also suggests us another way to select k people out of n people. Once we consider one of the person P is in the committee, is not in the committee. Yes, so this is the combinatorial proof, and this is known as the committee selection model. The way we prove it, it is known as the committee selection model. Yes, let's see some more questions based on committee selection model. NCK KCM is equal to NCM n minus m CK minus m. Think over it, take your time and try to see what is happening, and then you can see the justification which I am providing. So the left hand side says that out of n people you choose k, and then out of k you choose m. It means I have the information that out of the n people which are k people, and out of these k people which are m people. So I need two informations. One is the k people, and out of k m people. On the other way around, on the right hand side, what I choose is out of n I choose m people. Now I already know that these m should be the part of k people. So I need k people, but m has already been chosen. So what I need to choose k minus m now, and out of n minus m, because m is already chosen, so I shouldn't repeat them. So now you can see that both are equivalent. Moving further, let's see a quick question. NCK is n by k, n minus 1 ck minus 1. How do you prove this one? So if you observe here is that, then it is k times nk and n times n minus 1 k minus 1, or better to write it down, it is nck kc1, then n minus 1 k minus 1 and nc1. If you write it in this form, then you will realize that it is just the previous result where you put m is equal to 1. Yes. So we have discussed the committee selection model. Similarly, we will discuss one more model which is based on the binomial coefficients. So recall the identity which we had just discussed, and this identity suggests that if I choose this number which is 3c2, then it is the sum of 2c1 and 2c2. So it says that each number in this table except first and last in the row is the sum of two neighboring neighbors in the preceding. So if I use the concept of the previous table, then I can also see it like this. We call it Pascal's triangle, where it says that a person can traverse the blocks in the map of the street shown figure below. The person starts from here 0 0. If we traverse one block, then we increase the first term by 1, then 2, and if it takes a right turn, then we increase the second term. So that's why this is 0, this is 0, this is 0, and now this becomes 1 2 3, and now again 3, because he has taken the left turn. Total 6 blocks have been traversed, therefore 6 comma 3, where 3 are the right turns. Yes, so we label each street corner with a pair n comma k, where n is the number of the blocks traversed from 0 0 and k is the number of the times the right branch or the right turn has been taken. Yes, so the question comes that to reach to a particular point, for example 6 3 or any point nk, how many paths are there? Again the combinatorial problem, if I ask that to reach to 6 3, how many paths are there? So answer is quite simple, you may already know it. When I write 6 3, I wrote it in terms of the first left, second left then right, and then left. So these 6 positions shows that 6 blocks have been traversed, and out of which 3 are there. It means that to reach 6 3 I have to pass through 6 blocks, and I have to take 3 right turns, which means that there are total 6 positions, and we have to fit in 3 hours. So the number of ways to put or to select 3 items out of the 6 items, which is 6C3. So that's why it is NCK, number of the possible routes from 0 0 to NK is NCK. Now recall the same identity, and let's try to prove it using the block walking model which we have just discussed. Yes. So now left hand side shows that the number of the ways or number of the paths to reach NCK. So let's say this is the point NK. What does left hand side represent? So if I have to reach to this point, there are only 2 ways. Either I reach directly from here, or I reach from here. Yes, it means that in one case I take the left turn, in the one case I take the right turn. Yes, so if I have to take the left turn, it means I am at n minus 1k position, and I take the left turn. If I am taking the right turn, then I am at the n minus 1 and k minus 1 position. So I take one right turn, one block, it becomes nk, it means that to reach to this point, the number of the ways is cn minus 1 comma k, and to reach to this point, the number of ways is cn minus 1 k minus 1, and after that there is a unique way, so multiplied by 1, and then I add there, which is the right hand side. Yes, so let's see one more problem. So there are the list of the identities which are given in the book, so you can either remember them, and for many of them we will see also the proof either using the committee selection model or through the block walking model. So using the block walking argument, prove the following identity. Yes, this one is little bit tricky because the left hand side square is there, right hand side it's not. Yes, now what does the left hand side says? Left hand side says the number of the ways to reach to the point 2n comma 1. Yes, now the important observation is that the number of the routes from nk to 2n comma n is equal to the number of the routes from 0 0 to n minus k. So you take n minus k, and this makes sense because you either start from 0 0 to reach n minus k, you take these number of the right turns, n minus k right turns, and you pass through n blocks, again you pass through n blocks and take these number of the turns, so that reach to the 2n comma n. So the number of the routes from nk to 2n comma n is same as 0 0 to n minus k. Yes, if we make this observation, then we are done. So since both the trips go a total of n blocks with n minus k right turns. Okay, so if this is clear, then the number of the ways to move from 0 0 to nk, and then from nk to 2n comma n is cnk and cnn minus k. But we know that cnk is equal to cnn minus k, and that gives me the required answer. Yes, so it means that if you manage to see it as nc0 and ncn, this one is nc1 and nn minus 1, then the proof is trivial. This is how you have to see it. So we have used this identity that nck is same as cnn minus k. Using committee selection model, prove the following identity. Yes, how do we prove this? So if you see the left hand side, then you can say that there are n people and you have to either one person, or let's say first see the right hand side. So there are n person 1 2 3 n. Now you can say about this one, either he is in the committee, he is in committee, or not in committee. So there are two ways for it: in a committee, not in a committee; in a committee, not in a committee; in a committee, not in a committee. So total 2 raised to the power n. If all n are not in the committee, it becomes NC0 because none of them are in the committee. If one is in the committee, then we do not know which one is in the committee. Out of n, if only one is in the committee, it means only one says yes, all says no. Then there are NC1 ways to find that person, and that's why there comes the NC1, and so on and so on. So this is one way. The other way you can see is that the left hand side is the number of subsets of size 0, size 1, size 2 and so on, and the right hand side says that counting all subsets by whether or not the first person is in the subset, second is in the subset, and so on and so on. So again, if the right hand side is not clear, then it can be visualized as follows. Suppose there is only one person, so either he is there, he is not there. Yes, so 2 raised to the power 1 possibilities are there. These number of the sets are formed. If two persons are there, A not B, not AB, not A not B, it means 2 raised to the power 2 number of the sets are possible. Similarly, 2 raised to the power 3 sets are possible, and that's why if n persons are there, 2 raised to the power n sets are possible. This one is again a little bit difficult but interesting, so we need to show this identity. Take your time to get to the answer, and then you can see what I am proposing. So if you see this answer, then to understand it, you can see that on the left hand side there is r is fixed, and on the right hand side there is r plus 1, which means one more right turn is there. So if I have to reach to this point 7 3, it is 7 comma 3, what I can do is that I can mark this star. So this is 2 2 if r is 2, this is 3 2 4 2 5 2 6 2. And now how it works? So what I say is that I reach to 2 2, take a right turn and reach to 7 3. I go to 3 2, take a right turn, reach to 7 3. So after reaching to the star, I consider a unique way to reach to 7 3. But does reaching to the star covers all possible ways to cover to the 7 3? Yes, it is. For example, 3 2. So till 3 2 we consider all possible ways to reach to 3 2. After that, there are either you take the right turn, which we are considering the unique way. If you take the left turn, then this is already covered in all possible paths to reach to 4 2. So that's why left turn has already been covered in the next case 4 2, and right turn we are already covering, it's the unique way. So that's why you can see it as follows, that if you break the roots from 0 0 to n plus 1 r plus 1 into sub cases based on the corner where the last right branch is taken, then we obtain identity 8. Yes, two more quick questions. So this one says that find the sum of the following identities using this one. Now if you have to find this sum, one important observation is that you have to use the left hand side, and the left hand side, it means that we have to write down these terms in the form of NCR, then only it can be done. So for example, in the first case the general term is k minus 1 and k minus 2, which is actually p k3, but I need in the terms of c. So which is 3 factorial ck3. Yes, so it means that this identity can be written as 3 factorial common, then c3 comma 3 plus c4 comma 3 and cn comma 3. Yes, now see the identity 8. So this becomes 3 factorial cn plus 1 comma 4n plus 1 r plus 1. Yes, similarly if you see the other identity and if you see the general term which is k square, then directly it is not visible that how do we write it in the form of cnr. So it means that because CNR or PNR, the terms look like n, n minus 1, n minus 2, n minus 3, so on. So it's better that I want k, k minus 1. So I write k square as k, k minus 1 plus k. Then the first term becomes 2 factorial and c k comma 2 plus c k comma 1. Yes. So now the first is 1 square. If I put k is equal to 1, then k, k minus 1 is 0. So I start with 2. So 2 factorial c 2 comma 2 plus so on c n comma 2, and then it is c 1 comma 1 and goes to c n comma 1, because 1 plus 2 plus 3 and so on till n. Now again you use the identity 8, so it becomes 2 factorial and c n plus 1 comma r is 2, so 3 plus again r is 1, so c n plus 1 comma 2. So similarly these identities are very helpful in finding the sums. You can use any one of the identity which is most suitable, but you have to write down in the terms of CNR. So thank you very much.